And then again, put on my travel things to watch. So 6 hours. I go to do that. Your car, they buy a house.
Very well. Thank you very good morning, everyone, and thank you very much for coming. This is a happy occasion to have a meeting here with on Muons in Minneapolis. And my name is Maxim Pospelov. I'm a faculty at the school and at FTPI. We much appreciating everyone's being able to come here for despite a very busy end of the term season. We would like to thank our sponsors and in particular the Institute for Theoretical Physics, Fine Institute for Theoretical Physics, which is was created at the School of Physics and Astronomy in late 80s as a result of public and private partnership. We would also like to acknowledge the Simons Foundation, who extended its grant to the FTPI for organizing meetings and workshops, and some of you get modest support from us. That is due to the Simons Foundation. Now, some of you are first time in Minneapolis. You may not, you might be confused about logistics and have questions. We have wonderful staff to help, Alicia and Megan, and also you can ask any of the people on the organizing committee, Kunfeng, myself, Sarik, Yohe, and Jen. And since I'm at this point, we should all congratulate Jen on a happy occasion in his family, and we all admire his dedication to come to the workshop less than 1 week after the birth of his daughter. Very well. Now, the goals of the workshop is to bring together experimental physicists and theoretical physicists, and maybe some of us have the boundaries melted, well, but with diverse the backgrounds and with the interest in muon physics, which is, I think, rightfully identified as a possible direction to grow in particle physics in the future decades. And the idea is to bring brainstorm and maybe find new angles on various ideas. Maybe we can find the new physics cases to study with the existing experiments, or if we're super ambitious, maybe we can come up with new ideas for new measurements and new experiments. We have here the experts in high energy muon and meson sources, and on the experiments looking for muon lepton flavor violation. We have experts on precision muon physics, including muonia, muon G-2 and muonic atoms. We have experts on basically muon scattering and muon beams, and we have also presence of people working on muon colliders, both on the theoretical side of things and on the experimental side. We have this is hopefully would be one of the areas that will progress in particle physics in the next decade or so. And then we have, of course, lots of theoretical challenges in muon physics, and one of the most commonly acknowledged is, of course, the muon precision calculation of the muon G minus 2, and the theory should, well, is already using all the arsenal available to it to fix the number to the greatest precision, and we have a lattice QCD person among us, Tom, who's going to review that part. So the idea is to be interactive, not to be shy. So please ask questions and so on. I should also mention that we have about perhaps a couple of talks per day that are remote. Not everyone was able to come over, and we hope that this would work. We also have a Zoom link so that remote people can log in and ask questions. Now, as was suggested to me by Robert, on December 7th, there will be a long-awaited kind of report by the planning P5 committee, and it so happens that it coincides with the lunch break for us, because it's going to be at 10 a.m. at Pacific sort of California time. So we have arranged some of the sort of streaming here, and we will all learn about the exciting developments to be reported by the P5, hopefully.
Tomatoes?
Yeah, well, not quite. We'll have dinner on December 7th, and importantly, drinks before dinner, and let's have a productive workshop. I shouldn't be taking more time. Now we'll have a first talk that will be from PSI by Aldo Antognini, and this is going to be remote. So do this. Wow. Well,
yeah, but can you try to speak?
Hi, everyone.
Oh, yeah.
Okay.
Yeah, okay. Can you try to speak again? Just real quick?
So I apologize for not being able to be there. Do you hear me?
Yeah, good. So I think we're all set up. Just a few quick logistical announcements to make. If you haven't already, please upload your slides before the coffee break, before your session. If you would like to use your own computer, then just talk to me, Kunfeng, or Yohei. Also, if you're speaking, be careful of this ledge here. And for the people on Zoom, unfortunately, during the in-person talks, we won't be able to hear you. So please put your messages in the chat, and then we'll ask them at the end of the talk.
So we can start, right?
Yeah.
Aldo, the floor is yours.
Okay, thank you very much for this kind invitation. I apologize again for not being able to be there. So the title of my talk is Laser Spectroscopy of Muonic Atoms, and how from them we can obtain benchmark for nuclear physics, and how can we use these atoms to search for beyond standard model physics. So first of all, what are muonic atoms? They are a bound system, hydrogen-like bound system formed by a negative muon and a nucleus. So, and as you know, so the muon is 200 times heavier than the electron, and because of this, the muon is orbiting very close to the nucleus, so that the energy level of this atomic system are pretty much sensitive to the nuclear structure, and in particular to the nuclear finite size. Indeed, you can see in this expression, so you see the energy shift caused by the finite size of the nucleus. You see that this energy shift is proportional to the charge radius of the nucleus, the RMS radius of the nucleus, multiplied with the mass of the orbiting particle to the third power. And from this expression, you see that muonic atoms are very much sensitive to the nuclear charge radius, or the nuclear charge radii in general. So in the last 10 years or so, we have measured several transitions in muonic hydrogen, muonic deuterium, and the muonic helium-3 and helium-4 ions. And by comparing them with the corresponding theoretical predictions, we have been able to obtain the charge radius of the proton, deuteron, helium-3, and helium-4 with unprecedented accuracy. So in this talk, I will start discussing a little bit the situation in helium, and then at the end, I will present the present status of the proton radius. So the muonic helium experiment is very similar to the muonic hydrogen experiment in principle. So we start with a low energy muon beam, and we stop this beam in 2 millibar of helium gas. So the formed muonic atoms are formed in a highly excited state, and they quickly decay to the ground state. And only 1% of the totally formed atom reach the 2s state, which is the state that we need for the laser spectroscopy. And then we send a pulse to excite the 2s to p transition. This is what we want to measure. And if the laser frequency is resonant with this transition here, so the atom is excited from the 2s to the 2p state, and the 2p immediately decay to the ground state, emitting 8 keV X-rays. So we can expose the resonance simply by counting the number of 8 keV X-rays versus the laser frequency, as you can see on this right plot. So this is the principle. Now let me show the result regarding muonic helium-4. So what we have measured 2 transitions between the 2s1/2 and the 2p1/2 and 2p3/2 state. Here you see the 2 measurements, and by fitting the measurement, we have determined the centroid position with this accuracy, with an absolute accuracy of about 15 gigahertz. This is this is having a modest precision, limited by the fact that these transitions are very, very broad. They have a line width of the order of 320 gigahertz. So from atomic physicists, these are very broad resonances. That's why at the end of the day, we are limited by statistical uncertainty. Indeed, you see that our statistical uncertainty of about 15 gigahertz is much larger than the typical atomic physics systematics uncertainty, which are from 1 till 2 order of magnitude smaller. So we are completely dominated by statistical uncertainty. The atomic physics systematic is pretty small, simply because we are dealing with an atom which is strongly bound. You see that the binding energy is scaling with m, where m is the orbiting particle mass. We have to deal with a very small atom. You see that the Bohr radius is scaling like 1/m, so that basically the external perturbation do not affect the energy level of this atomic system. This is why we are insensitive to systematics effect. So now we have measured the so-called Lamb shift, which is the 2s to p energy difference. And this Lamb shift from the theoretical point of view can be expressed in the following way. Here you see this equation with three main terms. The first terms here is a sum of many QED contributions. You see some of them depicted here, with the most important one being the one loop electron vacuum polarization. Then the second term here is the finite size effect, which is proportional to the alpha particle radius to the second power here. And this contribution here can be simply computed assuming a vertex here described with the form factor. In this number here, we have also some contribution that include radiative correction to the finite size. And then the third term here, it is a sum of higher order nuclear structure contribution dominated by the 2-photon exchange contribution and the 3-photon exchange contribution. And these contributions here, they have the largest uncertainties, as you can see, for example, comparing the uncertainty of the QED contribution and this uncertainty here. So this is the theory prediction that we need to extract the alpha particle charge radius from our measurement. So at the end of the day, what we want to do, we want to compare our measured 2s to p transition is this one. We compare with the corresponding theoretical prediction. And from this comparison, we have obtained this alpha particle charge radius. This is the value that we have obtained using the 2023 theory with this recent upgrade. When we published some years ago, the charge radius was this one. And you see what happened in the last 2 years. So it happens that basically the theory uncertainty became slightly larger. It became 40% larger, while basically the value itself, it has not changed very much. So this means that somehow the theory seems to be pretty stable, pretty sound. The alpha particle charge radius that we have obtained from our measurement, as you can see from this plot, is in this case, in muonic helium case, is very much in agreement with the measurement coming from electron-helium scattering. This is different with the situation that we had back in 2010 with the proton radius. So in this case, we have perfect agreement between our result and the scattering result. Let me comment very briefly on the electron-helium scattering measurements. So what we need to measure to determine the proton radius is the elastic scattering of electron at helium nuclei. And so you measure this elastic differential cross-section. And from this, you can determine the form factor. And taking the derivative of the form factor at q squared equals 0 is giving basically the charge radius. This is the covariance definition of the charge radius. And you see that from this measurement, they have obtained a very precise value of the charge radius on the 5 per mil level or so. So why they can reach this precision? Simply because they have good data. You see here the extracted form factor versus Q. You see that the data are very, very precise. So they have to deal also with only a form factor, because the helium-4 nucleus is having spin equals 0, so there is only a form factor. This is a different situation compared with the proton case, where there are 2 form factors, and therefore we need basically to disentangle between the electric and the magnetic form factor. The helium case is much more simple. And the third advantage compared with the proton case, it is that the helium nucleus is having very small tail, because the charge distribution it is more Gaussian-like, while the proton charge distribution, it is more in the shape of an exponential distribution. And all these 3 facts leads to this good charge radius, to this precise charge radius. However, I would like to point out some caveat. Indeed, in these measurements, some proton information is used. So, for example, this data point, this blue data point that you can see here, this Otterman data, they are in reality cross-section ratio electron helium to electron proton. So this means that basically to obtain this form factor, some parameterization of the proton form factor is needed. So I think that the community should pay a little bit attention at this fact here. Another point that I would like to drive the attention, it is the radioactive correction. It was some years ago that this radioactive correction have been accomplished, and nowadays, and this is a good news, there is a new framework which can compute QED and next to leading order, and this is this program basically developed by Adrian Ziegler and co-worker. Okay, so the proton charge, the alpha particle charge radius that we have extracted from ionic helium, it is a benchmark from few nucleon theories. Again, here you see our value of the charge radius compared with the values as extracted from electron scattering. And on the right side, you see some theory prediction obtained from ab initio few nucleon theories. And you see that nowadays, the theories are having uncertainties, relative uncertainties of the order of 0.2%. Just to give a little bit an idea what is behind this type of calculation. So the idea it is that to calculate the charge radius, you need first of all to compute the form factor. So what you have to do, you have basically to compute this matrix element between nuclear wave function and the electromagnetic operator here. And now the nuclear wave function can be computed by starting from the nuclear forces, which in the modern chiral effective approach, it is expanded in 2n forces, 3n forces, etc. And you have to do a similar and in a similar development for the current operator. But recently there is really a large effort in the community to have a consistent derivation and regularization of the many-body forces and the nuclear currents, so in order to obtain the precision that our experiment is basically offering. So and when you have the form factor, then you take the derivative, and from the derivative of the form factor, you can obtain the charge radius. And this is basically how this charge radii here have been obtained. Okay, now let me move on to muonic helium-3. So we have just submitted this, we have just published recently, so the helium charge radius as extracted from muonic helium-3. So what we have measured there are 3 transitions, and you see the 3 measured transitions between the 2s state and the 2p state. Now we can parameterize basically these 3 measured transitions. So with these 3 unknown, basically the Lamb shift, which is the energy difference between the 2s1/2 and the 2p1/2 state, in terms of the 2s hyperfine splitting, which is this energy splitting here, and then the 2p fine splitting, and then the 2p hyperfine splitting given by these numerical values. So you see that we have 3 measurements, and therefore from these 3 measurements, we can determine these 3 quantities: Lamb shift, hyperfine splitting, and fine splitting. So the experimentally obtained fine splitting is in perfect agreement with the theory. And I do not want to comment on the hyperfine splitting because there are no theoretical predictions for the hyperfine splitting, and I would like only to concentrate on the Lamb shift. Similar to the muonic helium case, we can compare the measured Lamb shift in muonic helium-3 with the corresponding theoretical prediction, which clearly depends now on the helium charge radius. And therefore, by comparing the two, we can obtain the helium charge radius as given here in red. As you can see, we are totally limited by the theory uncertainty. In principle, we could improve on the helium charge radius by a factor of 7 if theory could be improved. And the theory is limited by this 2 and 3 photon exchange contribution, basically this higher order nuclear structure contribution. Also in this case, the helium charge radius that we have determined from ionic helium is in perfect agreement with the scattering result and is serving as a benchmark for few nucleon theories. So there are two ways to compute the 2 photon exchange contribution. So one, it is based on dispersion relation and data, similar to the G-2 case, if you want. And the other one, it is making use of few nucleon ab initio theories with chiral inspired potential. And the good point it is that the two approaches here are nice in agreement. Till now, I have just explored basically the connection between muonic atom spectroscopy and these nuclear and hadron theories. However, we have also to deal with this sector, which is the sector of high precision laser spectroscopy in regular atom like helium and helium plus. Let me concentrate on helium plus. So there are basically two ongoing efforts to measure the 1s to s transition in helium plus, in this hydrogen-like system. So their goal it is to reach an uncertainty of the order of 1 kilohertz, which correspond to a relative accuracy of the order of 1 × 10⁻13. And then you can, so in the future, we can compare the measured transition with the theory prediction, which is given here on the right side. And you can see that the theory can be expressed in terms of the Bohr structure, which is given by the Rydberg constant. Then we have QED contributions, and then we have finite size contribution proportional to the alpha particle charge radius, and then we have the nuclear structure contribution. So basically, by measuring this transition here, and by fixing the alpha particle charge radius from ionic atoms, we can then perform a very interesting bound state QED test. Because so the difference between helium plus and hydrogen, it is that the higher order contributions, which are challenging from the theoretical point of view, therefore which are interesting, are scaling with z to the 5th, z to the 6th, z to the 7th. So helium plus is much more sensitive relative to hydrogen to this interesting contribution. So what can we do also with the alpha particle charge radius? We could also use this to perform a CPT test. So there is an ongoing project proposed by Sven Sturm, and the idea it is to measure basically the Larmor precession frequency of this bound system, both of the positron and of the electron. So you see this is a bound system of, this is 3-body bound system consisting of a positron, an electron, and an electron bound to an alpha particle. So you put this system into a penning traps, and then you can measure basically the same location, so the Larmor frequency of the electron and the Larmor frequency of the positron. And this can be related to the G factor of the electron, the G factor of the positron, and then also to this ratio of charge over mass. That's why, and now to extract the G factor of the electron, in order to extract the G factor of the electron that can be compared with the one of the positron, you need to subtract the nuclear contribution arising from this alpha particle. And this is where our alpha particle charge radius can be used. So, and the goal of this measurement here, it is basically to push forward this CPT test by order of magnitudes. You see here it is a logarithmic plot, and you see that you can improve this quality like the G factor or Q over M or delta M by orders of magnitude. So maybe I'm skipping this for the sake of time. Now I'm moving on to muonic hydrogen. So you probably all know that, so there are 3 ways to determine the proton charge radius. And so the historical approach, it is from electron-proton scattering. The second approach is from hydrogen spectroscopy. And the third approach, it is from ionic hydrogen spectroscopy. So, and back in 2013, this was the situation with the muonic value here. So giving small values of the proton charge radius and all the other determination here in disagreement by about 5, 6 or 7 sigma. This was a situation back in 2013. Now we do a fast forward, and now this is the present situation in 2022. So you see here basically the charge radius from muonic hydrogen is given by this vertical line, and you see that nowadays we have many more charge radii which are consistent with the muonic results. So, and here it's only a selection of charge radii. There are many more charge radii in the market, but I have just plotted here a certain selection. Let me comment briefly on them. So here in red are reanalysis, so basically are proton charge radii obtained from reanalysis of electron-proton scattering data. The challenge that you are facing in this experiment is given here, is represented here on the left side. So to obtain the charge radius, you need to measure the form factor and then to fit and extrapolate to q square equals 0 to obtain the charge radius, which is the derivative at q square equals 0. And this is where the community is divided. So each group teaches to the other how to perform this extrapolation. And you see that indeed there are groups which give larger values, and there are groups which give values which are in agreement with the muonic results. Here there is another group of a charge radii obtained from electron-proton scattering experiment, but in this case they use a dispersion analysis. And the dispersion analysis allows a consistent description of space-like and time-like data, and is based clearly on a fundamental principle like dispersion, analyticity, and so on. And you see that this kind of analysis are always in agreement with the muonic measurement. And by the way, they were in agreement with us even before we published. So this is a prediction of 2007, and we published in 2010. So the next, what we would like to comment, it is this new electron-proton scattering experiment. Till now, I have presented only reanalysis of old electron-proton scattering data. This is a new measurement done by the PRAT collaboration in 2019. You see very briefly here their setup. They use a Windows-less target, and they use a non-magnetic calorimeter so that they can access very small angles, which mean very small q square. And from this measurement, they obtain a charge radius, which is compatible with the muonic result. So let me comment now on this point here, which is the proton charge radius as obtained indirectly from muonic deuterium. So the idea of the following: we have performed spectroscopy in muonic deuterium, and from this Lamb shift measurement, we have determined the deuteron charge radius given here. Then we combine it with the isotopic shift measurement in hydrogen, which is a very safe and a very precise measurement of the 1s to s transition in hydrogen deuterium. And from this measurement, you can determine the charge radii difference between deuteron and proton. And now combining these two determinations, these two measurements here, we can then obtain this proton charge radius. So this basically means that the muonic results are very much consistent to each other. And in other words, we are also providing a strong constraint regarding some BSM physics coupling to neutrons, for example. So, but the main point it is that there is perfect agreement between the two muonic measurements. So there has been also a lot of activity in the hydrogen sector. All the ones circled here in blue are new measurements in hydrogen. This is the old average value. And what do you see that the new measurement, generally speaking, they have moved towards the muonic value, if you want. There are still some tension, but generally speaking, they have moved towards the muonic result. So this tension could be mitigated if you allow for a kind of fifth force, a kind of Yukawa-like potential with length scale of the order of 34 Bohr radii. But this is clearly a weak theoretical prediction, but in principle, we could mitigate the situation in the following way. So there is also a very recent result from the group of Friedrich Merck at the ETH. So they have done a very beautiful experiment where they control the systematic of the Rydberg state. They have the systematic of the Rydberg state under control, and therefore they have been able to deduce for the first time so a competitive Rydberg constant value starting from Rydberg state. This is a determination which is completely independent of the proton charge radius, because they only measure the Rydberg constant. And here you see their determination of the Rydberg constant. It is this blue point here. And you see that this blue point here is very much consistent with the 2018 codata. So with the Rydberg value determined from the codata 2018 adjustment, which is including the muonic result. So basically the Rydberg constant determined from this group is consistent with the proton radius from muonic hydrogen. And at least it is favoring it. While with the previous proton radius, with the codata 2010 adjustment, you see that they have a kind of tension, if you want. You have to compare this ellipse here with this data point here. Okay, so muonic atoms, in the last 10 years, they have become a probe of beyond standard model physics. This is also thanks to the seminal work of Maxim and various theories, which try to explain at that time the proton radius puzzle and the G-2 discrepancy and so on by introducing some BSM theories. Nowadays, the room for this BSM physics, it's not zero, but it is pretty small. So, and this kind of theory, generally speaking, they are suffering from some tuning. So, for example, you have to have a fine tuning between vector and axial vector. And this theory, they require some preferential coupling to muons and theory and proton, and therefore they have some problem with UV completion and so on. So the room for BSM physics is pretty small, but muonic atoms can be used now to really constrain and to set limit on BSM physics. For example, in this new work of Frugiel and Pézet, they have used an effective field theory approach to constrain this coupling constant here, well, with this typical effective field theory approach. Okay, what is the impact of the proton charge radius? So now, starting from muonic hydrogen, we have seen that we can determine the proton charge radius with this relative accuracy, and this is clearly a benchmark for hadron theories. But what we can do, we can now combine the muonic measurement with hydrogen measurement. Basically, we insert the proton charge radius as obtained from muonic hydrogen into the theory of hydrogen, and from this, we can extract on one end the Rydberg constant, and you see that the Rydberg constant can be extracted in this way with a relative accuracy of 8 × 10⁻13. And by using at least two transition frequency measurements in hydrogen, we can test the hydrogen level energy level theory down to a relative accuracy of 1 × 10⁻12. The charge radius clearly is also of the proton and of the deuteron are also needed for the theory prediction of the most simple molecule, this HD plus molecule with a proton, a deuteron, and an electron. And by comparing theory and experiment, so the electron mass can be extracted, or to be more precise, the electron over proton mass ratio down to a relative accuracy of 2 × 10⁻11 can be extracted, or we can use so the electron mass as obtained from Penning traps measurement to test the HD plus theory down to a relative accuracy of 10⁻11. After having obtained the electron mass in this way, we can insert this in precision measurement accomplished with Penning traps, and from this we can test bound G factors down to a relative accuracy of 4 × 10⁻11. So what I want to say with this slide, it is just to show how a precise value of the proton charge radius is propagating in this various system, and how it can be used to determine very precisely fundamental constant and to test fundamental theories in hydrogen or in simple molecules and so on. So at PSI, we are nowadays initiating a new project. So we are preparing for the measurement of the hyperfine splitting in the of the muonic hydrogen in the ground state. So we would like to measure this energy splitting between this triplet and singlet state down to a relative accuracy of 1 × 10⁻6. And we are doing this for 3 main reasons. So first of all, we would like to measure, so from this energy splitting, we would like to determine this 2 photon exchange contribution. So and from this we will learn about some magnetic structure of the proton, about the magnetic structure of the proton, and this is linked with the spin structure program at the JLab, with a form factor problem at JLab and at Minds, and so on. So if we understand better this 2 photon exchange contribution, then we can try to combine measurements in muonic hydrogen and in hydrogen, to combine the 2 hyperfine splitting in hydrogen and muonic hydrogen, and in this way we hope to be able to test the hydrogen hyperfine splitting theory down to a relative accuracy of 10⁻8. And this clearly can be used to test or to search for beyond standard model physics. And with this, I'm coming basically to my conclusions. I can skip this slide. I have the impression I'm running out of time. So I'm coming to the conclusion, and I hope that I have conveyed the message that muonic atom spectroscopy are providing interesting benchmark for hadron physics, for nuclear physics. So understanding this nuclear and hadron contribution is leading to very precise tests of QED in hydrogen-like system, in simple molecules, and so on. And clearly we have exchanging a lot of, or we are advancing and triggering advances in this various field related with radiative correction, high precision laser spectroscopy, scattering, and so on. So thank you very much for your attention.
Thank you so much. Let's take some questions from the audience. Here.
Thank you for a nice talk. So I want to ask about the charge radius of the proton. I think you told us that the measurement of deuteron charge radius and isotope shift can, give a indirect measurement of the proton charge radius. So
Yeah.
how do you actually measure the isotope shift without knowing the charge radius of proton?
I mean, it is so the isotopic in the hydrogen. So what you are measuring in the isotopic shift, you are measuring the 1s to s transition. The finite size contribution of the 1s to s transition is very small. So you know it's you see immediately where is the resonance. So the hydrogen and the deuterium resonance are known where they are. It's not a problem to find them.
So basically, just look at the shift of the transition.
Measure the frequency difference in hydrogen and deuterium, and from this you can reconstruct this charge radius difference.
Thank you.
More questions?
Thank you very much. Nice talk. So you were discussing like a light nucleus, like hydrogen, deuterium, helium. If you go heavier nucleus, what kind of physics can you expect?
Nuclear physics. There is a program at PSI to I have skipped these slides, but I can maybe show this to you. So so we have a program to measure, for example, to perform X-ray spectroscopy in heavier muonic atoms. This is done with this is not a laser spectroscopy, but it's just X-rays. You just measure the characteristic X-rays emitted while a muon is cascading down to the ground state. And so the main motivation are related with nuclear physics, but there are also motivation to, for example, to know the nuclear charge radius of radium for atomic parity violation experiments.
Yes, thank you.
So maybe I can ask also a question. Aldo, you mentioned the G factors of normal helium, helium ion being measured, right? In the penning trap.
You mean, okay, yes, this new project.
Right. The question I have, is there any like reason to try to measure the G factor of the muon inside an atom? There is still going to be a polarization, a residual polarization after the cascade. Is there any information to gain?
I'm not sure I'm really getting your question. After the muonic state, the muon is depolarized.
But not fully.
By there is maybe 5% polarization, let's say.
Right. Yeah, but with intense muons, you could possibly measure G factors and of say helium mu minus, and that should also give you some information about I don't know the splitting and so on.
Yeah, but I'm not sure that we will be very competitive compared with the direct measurement. So we have no relativistic boost and so on. I don't believe that we will be competitive.
Okay. Well, thank you. If there are no more questions, we'll go to the talk number 2. Thank you very much.
Thank you.
We now have Kitano-san talking about new proposals with with the muon beams.
Okay. Okay, great. So thank you. I'd like to thank organizers for inviting me to here. It's very nice to be here in winter. I'm going to talk about some possibly crazy proposal of muon collider based on the mu plus beam. We name it as a muTRISTAN experiment. And this is talk is based on works done with a bunch of theorists, young people, actually, most of them live in KK, but anyway, and also including some experimenters, accelerator physicists, Yoshida-san, and yeah, bunch of students and postdocs. And also we are making a progress with experimentalists for the detector simulation and so on. Okay. So let me start with the motivation to think about the next generation collider experiment, the high energy collider experiment. And I think there are three very clear motivations to think of the next generation colliders. One is, I think we must investigate the form of the Higgs potential by the observation of self-interactions. You know, as you know, the Higgs boson has been discovered for 10 years ago, or more than that. And we found the standard model, but I think we are not confident with the form of the Higgs potential, which directly means indicates what's the origin of the electric symmetry breaking. I think that is the very important question that we should know. And so that's one of the things. And also we must check the possibility that one can actually produce dark matter artificially on the Earth. So we know that there are dark matter, and we don't know what it is. But there's a potential possibility that we can actually create it on the Earth, and we should do it. I think that's a very clear motivation. Second motivation. And third one, and we must look for new physics, at least up to about 10 TeV, which is kind of the one loop higher scale than the electroweak scale. I think that's where most likely something is hiding. So I think we should look for it. So I think there are three very clear motivations to go to higher energy collider. So I think the message is that we cannot stop here. We should continue this activity. I think this is very clear. So of course, there have been many discussions on what would be the next generation colliders, and high luminosity LHC is probably just happening, and they can measure the Higgs potential very nicely, like percent level measurement is possible. And there's also a discussion of ILC, the linear collider using the E plus E minus beam, and that is gonna even better precision measurement of the Higgs potential should be possible, like 0.1% level measurement. So this, would be a very nice opportunity to look for what's really the Higgs boson question. Okay. And of course, there are even more higher energy collider it is planned. One of it is like FCC or FCCEE or FCCPP, hadron, that can go up to 100 TeV collider. That would be very fantastic. We can create lots of Higgs boson, and also there's a possibility that we can really make the new particle by having this very high energy beam. And some other possibility would be the mu plus mu minus collider, maybe going up to 10 TeV or so. That will be very fantastic because first of all, this is small. It could, fit into the Fermilab site and even go up to like 10 TeV. So that would be a very nice opportunity, I think. And lots of Higgs boson can be produced at the mu plus mu minus collider, and of course up to 10 TeV, like meaning that 5 TeV new particle can be really produced. That would be very nice. So this is a kind of the fantastic future of our high energy program. And I'm sure LianTao is going to talk about a lot about the muon collider physics potential, but I just want to say that this is just fantastic. This is first of all very small. A few kilometer ring would be very enough for producing lots of Higgs boson or possibly new particles, and the reach is really like basically just any particle mass less than 5 TeV will be found. That very good. And also the Higgs boson is really clearly be seen even at the what is this? This is the previous 3 TeV collider, very clearly. So there you can do the very precise measurement of the Higgs boson couplings. Okay. So very nice. So then the natural question would be that why don't we just do it now? It's a fantastic collider and it's small. It's not so expensive. Then you should do it now. But of course, there are many technical challenges to realize this collider, and the most challenging part is to obtain the large enough luminosities. I think the next speaker is going to talk about this question a lot. But anyway, today's talk, I'm going to talk about the kind of possibly realistic scenario of only mu plus based colliders, not mu minus. We forget about mu minus and just think about producing mu plus a lot and use for the collider experiment. That's the proposal. Okay, so let me start with this famous formula for the luminosity at colliders. So of course the luminosity is proportional to the number of particles in a bunch. There are lots of particles and quite a lot. And of course, in the denominator, we have a cross section. I mean, these are size of the beam in a transverse direction, X and Y. So of course, the smaller beam, we can collide a lot. So that's the basic formula, and there's the repetition rate. How much collision in a second or so. Anyway, frequency of the collision. So this is the very simple formula for the luminosity. And if you just put some numbers, which sounds realistic, like number of particle in the bunch, let's say nanocoulomb. According to accelerator physicists, I think this is the realistic number, and beyond that, it's very difficult to handle because of the space charge effect and so on. So this is kind of the maximum number. You could probably go 1 or 2 magnitude a year, but anyway, this is a kind of the realistic number, 10 to the 10. And the size of the beam, we don't know how much we can do, but let's take microns. That's again the kind of the very, very small beam size, micron. And take the megahertz, that's the frequency. That's basically just fixed by the size of the ring, because we know the speed of light. So how many times we can make is fixed by the size of the ring, and let's take kilometers, then it's megahertz. So I think this is kind of the realistic number to put into this formula. And what we get from this number is like 25 inverse femtobarn per year. This is not quite enough usually for the precision measurement of the Higgs boson and so on. So, but anyway, this already any collider, it's just saying that if you want to go up to like inverse at one level per year or so, what you need to improve some of them or in this thing. For example, having a lot of bunch can actually increase this frequency, or maybe much narrower beam. Like at KK, we have a very narrow beam that gives you a high luminosity at the B factory. So that kind of thing may be necessary. But anyway, this having very narrow beam that's the most difficult part for muon collider, because the muon is produced with very spread, wide spread in momentum and also the space. So the cooling of the muon would be the key. I think this topic is going to be covered by the next speaker. But anyway, let me just say something that okay, the muon beam, conventionally, how it is produced is that okay, first proton beam, like J-Park, we have a proton beam, and we have a target which produce lots of pions, charged pions, and these pions gonna decay into muon 100% of time, but at the time of muon produced, it's very widespread because it's going through this pion, right? So the typical emittance for these produced muons are like millimeter size, millimeter size. But what we need is much narrower beam for collider. Anyway, I think Mibe-san is going to talk about this afternoon probably that how muon can be cooled is going to be explained a lot. This afternoon. And the conventional or the standard method of the muon cooling for the purpose of muon collider is the following. This is going to be again covered by the next speaker, I think. But anyway, I'm flashing the result of the mice collaboration that they do see the increase of the increase of the particles in the low emittance, so that they found that the principle of this cooling works. The principle is that just making muon slow down by going through some material, and the acceleration again gives you a lower emittance. So that's the principle. And the plan is that starting from this emittance, this is transverse and longitudinal emittance, and the emittance is going to be cooled down. I don't know what is going on here, but anyway, it goes up to like very small, how many 3 orders of magnitude lower emittance in the transverse side is produced, realized. That's the kind of the plan of realizing the muon collider. And that will be enough. But there's another method for mu plus. Not only, okay, so the previous method, this works both for mu plus and mu minus, but there's actually a completely different method that works only for mu plus. So there's something called ultra cold or ultra slow muon technology. That is to make muon stop. Okay, first, the first part is the same. Proton beam hitting target, pion is produced, but we stop that pion, and muon is going to be produced by the pion decay, but it is stopped. So it's very slow muon is going to be produced, but that muon, slow muon, again stopped. So it's stopped. But when it is stopped, what happens is that the muon actually catch electrons to form a muonic atom. Not the muonic atom, sorry, muonium. The mu plus forming, catching E minus to make like hydrogen-like things. The mu minus is actually at this stage just gone. Gone meaning that the mu minus is produced and stopped, but they are just absorbed by the protons or somewhere materials, nucleus. And once it is catched by nucleus, it's very difficult to get it out. But for the case of mu plus, they are catching electrons, so you can just ionize them by shooting laser. So stopped muon, you can actually get very cold muon out of this process. So mu plus, catching E minus, stopped, shooting laser, it's just a very slow muon. We can get out. Mu minus just gone. So mu plus, you can actually cool it down by this mechanism. And compared to this conventional or standard method, the emittance is just here. So it's very cold from the beginning. So of course it's stopped, so it's almost zero, right? So you can get very cold muon here. So why don't we just use this cold muon for the collider? I think that's a kind of the proposal. Okay, and let me mention a little bit about the G minus DDM experiment of KK. Mibe-san is going to talk about this whole thing, but anyway, I just say that they are actually making this experimental facility, and I think part of them is already built. And okay, so they do use that ultra cold muon to measure the G minus 2 of muon. So they produce, pion and stop muon and ionize, and we accelerate and put into the magnet and measure G minus. And that's just not a dream, it's just happening now. And they already demonstrated the cooling part of the muon, and also the acceleration part is going to be done maybe next year. So this is really the ongoing experiment. I want to say that this technology is just there. The cooling muon, it's just, cooled muon, they already have, we have that kind of cold muon already. And the accelerating technology is already, almost established. So the very, upstream part of the possibly muon collider is already there. So I think that's, interesting opportunity to think about this kind of experiment. muTRISTAN, that is, okay, we just accelerate that muon up to TeV. So this is kind of the prototype. We just designed this collider ring at the same size of the Tristan experiment, which means the KK, super KKB ring that we have. But anyway, I'm not going to say that we are really using that ring for this muon collider. Just as a reference, I took this 3-kilometer ring as a design. And 3 kilometers is a nice size because they can support TeV beam with a magnet we have. We have meaning 10 Tesla magnet. We can support the 1 TeV muon beam in the 3-kilometer ring. And because we only have mu plus, we should think of mu plus E minus collider or mu plus collider. And potentially mu plus E minus collider can be a Higgs factory because the square root S. Okay, so think about 1 TeV muon and hitting to 30 GeV electron. Okay, 30 GeV electron also we can actually manage it into this 3-kilometer ring. That is actually the original Tristan experiment that they do. And so the 30 GeV electron you can go around and collide with this 1 TeV muon, which gives you square root S to be 346 GeV. So we can do the Higgs boson production with this energy. And also 1 TeV versus 1 TeV mu plus collision can be possible. And that has some new physics, potentially new physics that should be possible with square root of S to 2 TeV. Anyway, this is just a design with this 3-kilometer ring. So this is just the number I'm just quoting. If you have much larger collider ring, we have higher energy possible. But anyway, this is the kind of the basic design. We have in proton driver, the same size of JPERC, and that you can produce lots of pion here and stop that pion and let it decay, and decay the muon, again stop, and shooting laser, we get the ultra cold muon and accelerate to 1 TeV. So this is the kind of the basic design of this muTRISTAN experiment. So there's a simulation work going on, how much cold muon we can get for colliders. And this is a kind of the very primitive design of this system. But anyway, proton beam is coming here and hitting the target. We put up lots of layer of tungsten, so that make it pion stopped. Okay, for this simulation, actually, this is very large, like 5 meter, very big facility. So almost all of the pion is stopped somewhere. And there's a muon stopper inside this, in between this layer, and that make it stop, produce mu plus, and they form muonium. And we shoot laser in between these layers, and that makes it ionize muon, and we can correct it by the static electric potential. So this is the kind of the basic setup, and they calculated, they mean that, okay, so Yoshida-san and Sakaki-san, they are the accelerator physicists, they are doing a simulation, and according to their simulation, they can get the number of muon to be like 10 to the 14 muon per second level. So this is huge. This is 5 orders of magnitude bigger than the current JPEG muon line. So but anyway, according to their simulation and basically just efficiency calculation gives you a similar number that 10 to the 5 larger muon, super muon factor is possible. So the all ultra cold muon is possible. So this is actually big enough number for the collider purpose. So we can just calculate the luminosity by using that number of muons, and we assume 40 bunches, and a bunch of things we assumed, like beta function and so on. But anyway, we get microns of beam and also 10 to the 10, and the 40 bunch helps to make it megahertz, so that we get like at one level, inverse at one level with 10 years of learning. So this is kind of the nice goal of this. For physics purpose, I think this is kind of the necessary luminosity, and that we can manage it with this technology. And actually, these numbers are quite very conservative. People would say that, okay, this is much smaller than the muon, acceleration map program and so on. But actually, in this parameter, we are actually taking a very conservative one, because we are thinking of this collider would be very good if we can make it earlier than the usual muon program. So we make it very conservative for this estimation. So this is actually the theorist estimation of how much luminosity compared to the map. Map is a muon, now it's called IMCC or whatever, some muon acceleration, muon collider program in the US and Europe. And compared to the muTRISTAN, mu+, the emittance is much better at the muTRISTAN because we stopped the muon. And also bunch length, we can make it shorter. But the efficiency to collect muons, we have, we can't get so much because we stop by muon. So many muons are going to decay. And also there are many, efficiency comes in, like how much efficiency for the ionization. So we lose this one, but just collecting this number and normalize with this muon acceleration program, what we get is that I think the luminosity is higher, potentially many order of magnitude higher than the usual mu+ mu- collider. So I think maybe with just existing technology, we may get a larger luminosity. Of course, this is mu+, mu-, and this is mu+, mu+. It's different, but still, I think it's an interesting possibility that if you use this ultra cold muon, we may have a better chance or better luminosity for these colliders. Okay. So the question is that what we can do at this mu+ based collider, like mu+, E-, mu+, mu+, what we can do. As I said, the Higgs production is possible through the W boson fusion process, and compared with calculating the cross section, we can get like 10 to the 5 Higgs boson productions are possible, and also the Z fusion and so on. But anyway, the 10 to the 5 Higgs bosons that less than % level precision for the coupling is possible. It will be possible. And also mu+, there's no direct WW fusion because charge doesn't match. W+ and W+ can't go to Higgs boson, but there's actually one order lower, higher process. First emitting photon and W+, W- splitting, and W- can get the W+, W+ fusion process to Higgs boson. This process is possible. And this actually is not so small. It turns out that at very high energy, this process is, grows really fast at the energy. So this may be an interesting process. But anyway, in both of the colliders, I think 10 to the 5 Higgs bosons would be possible with this luminosity. one of the interesting things of this mu plus E minus collider is that it's very asymmetric. So mu plus is 1 TeV, E minus is 30 GeV. So all the produced particle actually goes to the mu plus direction. So the detector should be covered in a forward region. So this gives you some challenge for the design of the detector, but it seems that the conventional design, like high luminosity LHC, would be good enough. Like what we want is like eta to be 4 level forward coverage, but eta to be 4 is already covered at the high luminosity, so it's maybe not so bad. So the Higgs coupling measurement, as I already told you, that the 10 to the 5 Higgs bosons gives you like sub% level measurement, like 10 to the minus 3 level, 3 times 10 to the minus 3 level measurement would be just possible by just counting the number of Higgs bosons. So by the way, this is the BB bar channel, and the red is the Higgs boson, the blue is the Z boson, and we can really see the Higgs boson by using this thing. And also Z boson fusion may be also interesting, because Z boson fusion, we don't have to look at the Higgs boson decay. We just need to look at this forward mu and the forward electrons, and we see there's a huge background from the Z boson production, but it looks like we have Higgs boson excess around here. So recoil measurement may be also possible. And these kind of simulation actually depends really on how good is the calorimeter in your system. And if you actually use the Atlas card, Atlas detector, okay, this is very fast simulation. And this is the high luminosity LHC Atlas detector. And this is the conventional LHC Atlas detector with a large forward coverage. We just modified a little bit, but it's really different. You really see the 2 peaks of Z boson, the Higgs boson in this case. So with conventional one, somehow the conventional meaning that the current LHC card has a better resolution. How much time do I have actually?
Well, time is up, but we.
Okay. Well, anyway, okay. So sorry. Yeah, if you change the dicta, the shape is really different. So sorry about that. Well, okay. Let me just. Yeah, I think mu plus collision, as I already told you that this W fusion process is possible, and actually the cross section grows a lot. So that with 10 TeV, actually it's bigger than ZZ channel, and the cross section is actually not so different from the mu plus mu minus collision, because as you know that the mu at very high energy like 10 TeV, it doesn't matter if it's mu plus or mu minus, because anyway it's called lots of gauge boson is going to be produced. Sorry about that. So yeah, and also new physics program, we can run dark matter production. That's also interesting to do. And there are potentially, the mu plus, there's a mu plus mu minus study, but actually this gauge boson fusion channel, the dark matter production is the same for mu plus and mu plus. So we can do the same thing, so on. And muon specific flavor physics, and also the contact interaction we can actually do the mu plus, and so that gives you a nice search for the physics. Yeah, okay, let me summarize. So I want to say that the mu plus may have a better chance, maybe meaning that the better chance to have collider earlier than the mu plus and mu minus. And if that's the case, I think it's interesting to consider starting with a very small, like kilometer size experiment as a relatively near future project. I think that would be nice to have soon. Thank you.
Indeed, it would be very nice to have. So let's have questions. All right.
Thanks. Nice talk. 3 quick questions and a comment.
So this might be for the later speaker, but I was very impressed with the 10 to the 5th Muon collection. So why don't you use that in the cold G-2? Right? Why can't you use that in the cold G-2 experiment?
Right now, you mean?
Yeah.
Yeah, of course. Yeah, maybe that's for Mibe-san, but
Right.
I think, first of all, of course, they can't support this large mu, I think, in this experimental setup. I think, well, I don't know actually, but I think it's,
The question is interesting that you can get a lot more fires initially in the
Right.
muons, right? But
Right.
there are other parts of the
of course, yes,
ecology.
yes,
Right.
Muons and ionizing this, whether
Yeah.
this is going to work or not.
Right, I don't know,
That's-
but it's an obvious question to ask, right?
Yes.
yeah, I think there must be some interesting experiment done at the upstream, I think, if this is built, I think.
The second question is do you have a neutrino radiation problem?
That's the same as the usual.
Okay, so you still haven't solved that. I guess all the backgrounds from physics from
But
imaging-
anyway, it's not actually, it's
well,
a little bit
Japanese
better.
neutrino radiation might be
But
different.
it's
from
a little
American.
bit better because the bunch charge is smaller. So
Yeah.
yeah, but it's almost the same. Yeah.
Yeah, and I guess things like the beam induced backgrounds
Mm-hmm.
with the detectors are the same.
Yeah, that's the same.
So looking at this, one thing, and this is a quick comment, and then I'll turn it over, is that it would be really nice, like, you know, when the ILC people come forward, right? They show, oh, we can measure this gauge coupling to this, and, you know, stupid, you know, PP machines can only do this. It would be nice to have a table of what you can do versus what a
Right.
muon collider could do, and just a table that
Yes.
any idiot can look at and understand.
That's yeah, very high priority. But one comment is that I don't think it's fair to say that okay, ILC can measure this one separately. But as a theorist, we don't care, right? if one of them is deviated from standard, that's nah. I think that
We gotta keep it fun.
But anyway, so that's very delicate issue how to compare those kinds of things. I think that's one comment here.
While I'm walking to this part of the room, I can ask my question. So have you looked at, say, mu plus to E plus E plus, or mu
Yeah.
plus mu plus to tau plus?
Yes, yeah, that's the one I skipped.
Okay.
Yes, lepton flavor violation. That's one of the interesting opportunity. Where is that? Yeah, this is one. So this is mu plus to tau plus, and the compare with some other experiment fixing some model.
Can you access muonium and anti-muonium size of the operator, right? Because like if you have mu plus to E plus, right, this also leads to muonium to anti-muonium oscillation.
Yeah.
So if you, it would be neat to see if you can
Right.
improve over that.
Yeah, but usually muon, low energy muon experiment gives much better.
But this is muonium. You
Right.
pay price
That's right, yeah.
for the weight.
So for the case of tau, I think it's much better than tau factories. I think.
Okay, so I have a couple of comments. So first of all, thanks for the fantastic talk.
Thank you.
So let's say with my muon collider hat on, I think that muon collider people are not married to the ionization cooling concept. We just want to get a collider on the ground. So this is fab. This is really good. And if this is the one which works, then who cares, right? Who cares about the accelerator? So that's my first comment. But then just thinking about your luminosity slide. So you commented that 10 to the 10 muons is like a space charge limit. So that's not quite right.
Not quite right. Okay.
So in a collider ring, let's say space charge is really strong at low energies, but at high energies, space charge is not such a big deal.
I agree.
So in the collider ring, in fact, space charge is not the limiting factor. The limiting factor in the collider ring is beam-beam interaction. And so that limits the maximum current. And so 10 to the 10 is let's say low for a collider ring, but then when you look at the low energy part of the facility, that's where you start feeling space charge. And then the question, maybe a question is whether you've done the space charge calculation for the very low energy muons where they're basically stationary when you manufacture them. Can you maintain this low emittance, or does the beam get blown up by space charge?
I mean, okay, so I think that is very much related to Mibe-san's work. They are really doing that experiment. And the question is whether or not this acceleration gives you a enlarge of the emittance.
But you need 10 to do it experimentally. You need 10 to the 10 muons. This is
Oh yeah. Okay.
This is
That's
only
right.
a 10 to the 5.
That's true. That's true.
So there's
Yeah.
no space.
Well, we haven't done anything dedicated to simulation yet, but we just scaling this 10 to the 5 smaller experiment. We are just assuming that no growth of the emittance in this stage. Of course, it may not be so realistic, but we should think about that. Yes.
Thank you.
Yeah, maybe I can ask about the MUE option. So you said that in that case, the collision is asymmetric in energy. So how much narrower do you have your detector kind of gap to be? Because I'm assuming if it's forward, you need to kind of go more forward in acceptance.
So
that means more beam-induced backgrounds usually, right? So then how do you avoid that?
Beam-induced background. Yeah, that's.
So if you have a 1 TeV muon, right, and your center of mass collision is 300 GeV, those positron emissions from muon decay presumably overwhelm your.
So we haven't worked out that beam-induced background at all. but anyway, we are. The coverage is like 2 degrees. That is the necessary angle that we should. And what is the tungsten shield is usually 10 degrees, but this is fortunately this direction. It's muon is coming from here, and the event is going this way. So the shield doesn't interfere with that. But beam-induced background, of course, you have to think about carefully.
Thanks.
That was my question. Okay. So then we probably ran out of questions, and let's thank Kitano-san again. So we now have a break, right? So let's reconvene 5 past. 11:05. Okay. We're going back.
Yeah, I mean, Mateos, by the way, it's nice to meet you. Yeah, it's an issue, right? So you have a nice symmetric muon collider.
Spaces between this is outer gradient. It's not. Surface as the sort of crazy. You mean you only have 5 meters from one side, but they're not. They'll have to be shooting. One micron.
Then you have more sensitive mass energy.
But it's not from the collision. No, it's not from the collision. It's just that the beam background is along the beam. I think it's all that. So the other is
come closer to.
It's a very soft part.
We can't be blind because they don't get into the. There's a lot of interaction between the different experiments. So finally, you know, and all this.
So it's not like a cheap matter.
That's
Actually,
It's pretty soft. Occasionally you get some, but it's very, very soft.
Now,
It's not like it's a.
The 300 is
Just getting that
let
thing
me just.
Yeah, that's why they can get rid of it with a bunch of tungsten. Right?
Yeah. So the tungsten is still there.
Now.
It's on
Yeah.
there. That's what he said. It's the event going that way. Tungsten is.
Thank you.
Thank you very much.
Yeah.
Quite a lot.
Leave the site is the one that way.
Those are your.
Yeah. Because it's where you live. Yeah, convincing your neighbors. My argument is, well, if you share one, the camera.
It's a share.
Welcome to the multi.
This.
Because your house would be.
I think we're probably good to
Yeah.
go for the next.
So it seems that the new minus, there's also a study how to
Share
get
the next one.
Yeah, the mu minus, the mu, or the mu minus by why is stripping, you know, Muonic helium nuclear. Why? That may be possible. Okay, again, stop the muon first and accelerate and putting, yeah, I think Muonic, mu minus, mu minus helium, that accelerate and fix, that's the one possibility.
Yeah, I get you can modify.
The another.
Yeah.
这个就好了。
这个比那个周四食物应该好。
对，这周四饼干好像。这个一个可能行，但可惜不是酸奶，好酸的。酸奶。
Great, okay, yeah. Yeah, I'll show the cards. Yeah, so pointer here, slides forward to backward. And I'll show the little time card for 5 patterns and 20 patterns.
Okay, good. And I will try and do my best. Yeah. 25 minutes, I think.
Yeah.
Yeah.
Okay. Okay, morning, everyone. Welcome back to the second session of this morning. This session, we talk more about the high-energy muon colliders. And first, we have Chris Rogers give us talk about production of high brightness muon beams. I hope I need some stimulus because I didn't have enough sleep. I hope the workshop is interactive and people should ask questions during the talk. We don't need to necessarily say every question till the end.
Yeah, I'm happy if people want to ask questions, of course, just far away. That's no problem. So, okay, so production of high brightness muon beams. Yeah, so I think this is true. I just paused a second there because I was thinking, is this true of the muTRISTAN as well? But I think it is true of muTRISTAN as well, right? So production of high brightness muon beams requires a proton source, pion production and capture, and beam handling and cooling. So that's what I'm going to talk about now. I'm going to talk in the context of 2 different activities. One is the ISIS upgrades activity, and then the other one is the muon collider, and specifically the muon collider, which the MAP program developed, and IMCC, which is at the moment European activity, but we hope it's intercontinental. The plans which the muon collider people are developing. And I'm going to focus on technology R&D aspects. I'm not going to talk much about the beam, about the particle physics. So let me start then. I'm going to start with ISIS. So as I said, we need powerful protons to make muons. So ISIS, I come from ISIS, right? So I feel the need to advertise my facility a bit. But also there's some R&D which we're doing, which I think bears on the muon program. So ISIS is the most powerful pulse spallation source in Europe. We make neutrons for neutron scattering. We're short. We also make short pulse muon beams. So we have a pulse length of about 60 to 100 nanoseconds, and in that pulse we get sort of few orders of magnitude of muons. We're looking now at an upgrade. I think there's a growing interest, I would say. So let's say the facility, I think, is probably more driven by the neutron side than the muon side. And in Europe, there is what people call the neutron drought, which is here and is growing. So there's a new facility which will open in the next few years called the ESS, which will be another one of these high power neutron spallation sources. But even with that new facility, there will still be a lack of neutrons. There's more facilities closing down than opening up. And the MUSR lines which we have on ISIS are oversubscribed. So we're looking now at 3 upgrade options, I should say. So there's 3 possible upgrade paths which we're looking at. One is the rapid cycling synchrotron. So that's similar to the sorts of things they do at JPark and Fermilab. Another option is a LINAC. So we accelerate the beam using a LINAC, and then we accumulate the beam in a ring, which doesn't have any acceleration in it. And that's like what they do at SNS. And then the option which I think is possibly interesting is the fixed field alternating gradient accelerator option, which we're looking at. And overall, our aim is to get to megawatt scale pulse beams, where they change the specification every now and then. It was 1 megawatt last year. Maybe it'll be 2 megawatts this year. So, but that's where we're looking for. So the RCS and the accumulator ring, rapid cycling synchrotron and the accumulator ring are attractive options. We can meet the requirements despite the usual sorts of issues which they have. So foil heating, managing space charge, for example. The downside of these 2 options is they require quite significant wall plug power. So that means the amount of electricity you pull off the grid, which talks about your carbon footprint, which is very important in Europe, and also talks about and elsewhere, of course, but also talks about your operating costs. Can be rather high for these sorts of facilities. For example, for the synchrotron option, we're looking at 2 stack rings. But they are well-known solutions. So the alternative which we're looking at is the FFA. That's quite interesting. The power requirements are likely lower because we don't have pulse magnets. We don't have a power-hungry LINAC. It's quite versatile as an option, but it's less well established in the field. So to try and promote the FFA option, try and understand the technical limitations there, we're looking at building a test ring. So that with that test ring, we would like to demonstrate high intensity operation, control of tune, charge exchange injection, and fancy injection of the protons and H minus, and longitudinal dynamics. And the key to the FFA technology, which we're looking at, is these wide aperture dipoles. And the way these things work is you have a higher field in the high radius and the lower field at the low radius, and that way you can keep your beam in the ring as you accelerate. And then one of the interesting things which we're looking at is this stacking concept. So what we want to do is push the available proton beam current, and of course that's important for muons as well as for neutron production. And so the fundamental limits which we have, so the oil heating is one fundamental limit, target heating is another fundamental limit on the proton beam current, but the other one which we're addressing with this technology is space charge when we inject into the ring. So the concept is that we inject many times, we accelerate the beam, we store the beam. Now, when we inject, so we inject the first time, we accelerate using RF cavities, that's these oscillating electric field cavities to accelerate the beam. And when we inject the second time, we can bring the beam up, and the oscillating RF, the beam is changing frequency as we accelerate. That means the RF cavities here are not coherent with the beam which is rotating up at this top energy as a function of time. So that means that this beam doesn't mess up the orange beam, if you like, doesn't mess up the red beam. And just to sort of so the only time they can interfere with each other is when we get right up to the top energy here. And so this is an example of how we accelerate the beam up. We put these blue particles, let's say we want to put them next to the orange particles. Again, this is energy, this is phase of the RF. And so when we get close, you can see that the RF from this beam here is actually interfering with the circulating beams, and that causes a little distortion. But if we're careful and we do what we treat the beam carefully, we can stack these two beams right next to each other. And that way we can get to higher currents. Okay, so then in terms of technology development to deliver this FFA option, let's say we're looking at two different technologies. One is the FFA magnets themselves, and then the other one is very wide aperture, low frequency RF cavities. So let's say we have a 3D magnet model which we've developed. This is COMSOL. We have an opera model and a COMSOL model, in fact, which are two different magnet modeling codes. And so the way we're developing these magnets is we have these because remember we want high field out here and low field in here, and we would need to tailor the field rather carefully across the aperture of the magnet. So the low energy protons, let's say, would circulate through this region, high energy protons would circulate through this region. And so we have these funny, I don't know if you can see them, these little trim coils across the aperture. And those are designed specifically so that we can tune different regions of the magnetic field differently by powering the coil these trim coils differently, over here compared to over here. And so we're developing the magnet at the moment, and we plan to build a prototype. Okay, and then the other thing which we're looking at is the RF cavities. So we need to build rather low frequency RF cavities. They're actually similar to what we have in ISIS at the moment, but they'd be much wider aperture. Now, these RF cavities work. They have a standing electromagnetic wave inside the cavity. The wavelength, the sort of frequencies we're looking at, which is roughly 2 to 4 megahertz, naturally is several hundred meters. So if you want to fit a standing wave inside an RF cavity, what you have to do is you have to use blocks of ferrite or magnetic alloy, Ma, and that's like has a massive refractive index. And so that means that the standing wave, the wavelength instead of being hundreds of meters, becomes sort of order a meter or two. So you can somehow then fit your beam in the ring. And if you want to vary the frequency for whatever reason, you as you accelerate the beam change, the beam rotates around the ring with different frequencies. So you need to vary the frequency, and you can actually change the resonant frequency of the ferrite, for example, by running a current through it, which changes the magnetic property, or putting a magnetic field across it. So let's say we're developing these RF cavities for use in a test ring. Okay, then the reason why it's relevant, the reason why I've got into this sort of dalliance into protons, is because it has applications in the muon world. So especially the development of the FFA magnets as a general technology, being able to tune the field profile is quite nice. And so we're interested in applying the FFA technology, the magnet development, the RF cavity development to, for example, rapid acceleration muons to muon collider, muon storage rings to neutrino production, and I didn't put, that was careless, and also prism and the advanced muon facility technology. Right, okay, so that's protons, right? So you have your protons. Now you want to make them into muons, and now we talk about the muon collider more generally. So as we heard from the previous speaker, the muon collider is a potential shortcut to the energy frontier. We can get multi-TeV collisions in a next generation facility. We can combine the precision potential of E plus E minus with the discovery potential of proton-proton. So there was some talk in the Q&A, especially about the neutrino beams. Now, the neutrino beams are a blessing and a curse. So they're a curse because they can make a very low level amount of radiation, but still it can be, let's say, it can be a hazard to health. So the level of neutrino radiation which we make is enough that if one were to lie down in the neutrino beam, which is about that big, if one were to lie down in the neutrino beam for a year, then we would be, let's say, outside the legal limit for radiation. So that's the slight concern. So it's a blessing because actually we can do some quite interesting physics with that neutrino. And no one has ever made a neutrino beam with anything like the flux or the energy of the neutrino beams we're proposing to do. And so actually what we would do, I mean, where the neutrino beams are coming from is let's say just around the interaction points we have a straight. In that straight you make lots of neutrinos from muon decays, of course, and they come flying off and intersect the surface at some point. And so actually what we would do is build a neutrino detector somewhere off on the surface and potentially do neutrino physics there. So that deals with the problem, and we get some nice physics out of it. The other thing to mention is that we get rather high flux, rather precise muon beams at low energy as well. I just put some parameters for the typical beams which we're talking about. So we have of order for the IMCC one, let's say we have 10 to the 12 muons per bunch. We have a rep rate of about 5 hertz. The beam power in the collider, so this is the muon beam power in the collider, is 5 to 10 megawatts, depending on what energy we go to. The longitudinal emittance we're talking about is 25 millielectron volt seconds, and the RMS emittance transverse is 25 microns. These are like this is like the length of the bunch, and this is like the transverse size of the bunch. Okay, so in terms of the technologies we need, maybe I should just go through this. So we put protons, we put them onto a target, we make pions, the pions decay, we make muons. Then we have to do something with those muons because the muons coming off the target are a real mess. We have to collect them using ionization cooling technology. We accelerate in some low energy, relatively low energy acceleration up to sort of 50 GeV type level. And we accelerate in rather higher energy acceleration, which up to TeV scale. So just going through the technology, I'm going to focus in this talk on this region here, the lower energy region. So this is the target system which we're considering. So we take protons down here, put protons into the target, they make pions, the pions make muons. For the target we're considering at the moment, the baseline would be graphite. In terms of heat load and power deposition, the target looks rather like T2K or something like this, or Dune. Probably in terms of our heat load, we can afford a slightly higher radius beam. So the damage to the target is actually not as severe as it would be on one of those facilities. But the challenge comes because we want to wrap the target just like muTRISTAN and Comet. We want to wrap the target in a solenoid. And so we want to go to a rather robust solenoid, so 20 Tesla solenoid, which would put us on the same scale as, for example, one of the fusion facilities like ITER in terms of the scale of the magnet, scale of radiation. The challenges in this target, so the solid target lifetime is always an issue with these things. Also, we were a bit worried about the windows upstream of the target. And then the other big issue, of course, is shielding the solenoid and looking at the energy deposition of the solenoid. And we're obviously looking into this quite actively. In terms of the magnet technology, we're looking very much at let's say magnet technologies which can manage this radiation load. One we're looking at, which we think is quite promising, is the concept of having a force flow cooled high temperature superconducting cable. The reason HTS is good is we can operate at 20 Kelvin, which means that the cryo plant can be much more efficient. If you try and cool helium down to 4 Kelvin for a low temperature superconductor, the cryo plant becomes much more power hungry in terms of the electricity you pull from the grid. And the other advantage of HTS is you can get the higher current densities, so it can have a smaller footprint and smaller stored energy. Obviously, for this sort of technology, there's a lot of interest from the fusion community, and there's a lot of interest from the ultra high field magnets for sort of MRI type. And then one of the worries we have with this technology is radiation hardness. It's relatively new. We're working to understand the radiation hardness. Okay, then as an alternative for the carbon target, we're looking at using fluidized tungsten and also actually a liquid metal target. So the concept behind the fluidized tungsten is you put tungsten powder on a helium bed, and then you use the helium to push the tungsten powder through a pipe. So this is sort of schematic of what the tungsten circulation would look like, let's say. And so in terms of the challenge of the helium bed, you have to lift the tungsten, which has rather high density grains. You have to lift the tungsten up to recirculate it, and then you have to push the tungsten down through a heat exchanger to get the heat out. So obviously it's getting heated by the beam. And so again, we think that this is probably possible. It's quite interesting because in principle, if we want to go to higher beam powers than the 2 megawatts we have in the baseline, this would be able to survive much higher beam powers. And also it's promising, in fact, as a neutron spallation target, because the target material is much denser. In principle, you get a smaller spot size. It may increase the muon yield from the collider as well. Okay, so ionization cooling. Good. Right, so in ionization cooling, the beam loses energy in an absorbing material. So let's say we put our muons, they're going all higgledy-piggledy, coming off the target, let's say, in the capture, and then we put them through an absorber and an RF cavity, and what we're trying to do is make them go in a straighter line. So we slow the muons down, then we re-accelerate them only in the longitudinal direction, and in this way, we can reduce the transverse and indeed the longitudinal beam emittance. The problem is that as the muons go through the absorber, they scatter off the atomic nucleus, and that makes it hard. So we have to use low Z material, so the atomic nucleus is small, and we have to use very tight focusing, so the transverse momentum of the beam is large compared to the scattering which we get off the nucleus. Oops. So this is the schematic we have. So this actually is similar to the plot which the map people produce. We're building on the map design. Oh dear, Some of my plots have got messed up, I apologize. We're building on the design which the map colleagues produced and extending it. So what so the way we work, the way this scheme works is we start off going through a cooling system which looks like this, with RF cavities sitting inside these magnetic fields. Magnetic fields focus the beam down off the absorber. And we can cool the beam down. Just to clarify, the reason there's this dotted line here is because we start off with 21 bunches. We cool those bunches down quite aggressively. And once they're at low enough emittance, we can merge all those bunches up into one single bunch, which gives us high luminosity. We get highest luminosity by having a high instantaneous current and few bunches rather than lots of bunches and a low instantaneous current. So that's why we want one bunch. That's why we go through this bunch merge. The emittance goes up because we painted this beam across the phase space, but then we can cool it back down again using the same system and finally get down to here. And then the optimum for luminosity is to get very low transverse emittance, but actually relatively large longitudinal emittance. So we can cope with a slightly longer or higher energy spread bunch, but we can't cope with a large transverse beam size. So we actually let the beam grow in longitudinal emittance and reduce down in transverse emittance, and that's what's going on over here. And we do that using very high field solenoids. That'd be 40 Tesla solenoids. So let's say the commercial solenoids, you can get 28 Tesla. We would want to go up to 40 Tesla here. So that's an R&D.
So Chris, it's the end point of the cooling curve where I have my high energy muon collider.
So the muon collider is here.
High energy muon collider required.
So it's a good question. So when they talk, Higgs factory isn't popular at the moment because it's probably not competitive with the E plus E minus people. But if you did want to do a muon Higgs factory, we can do a very good Higgs width measurement, better than the E plus E minus. That's the only one we can do better than E plus E minus. But if you did want to do a Higgs factory, you would stop here because that's so this is the longitudinal emittance, remember. So you want the minimum longitudinal emittance so that you get a very narrow beam in energy. And that way you can measure the muon, you know, when your muons collide, you can measure the Higgs energy, which you produce very well because you just know the muon beam energy to start with. And so there is a motivation of stopping here for low energy muon collider. But probably if you were going to build a muon collider, you would just go for a TeV or two and be done with it.
Yeah, there's no direct way to go to the endpoint of the right curve. I have to go through this low point and then come back.
That's what it looks like. It's, you know.
So his factory is free. it's the ideal cooling.
Higgs factory is free. And the other thing which is free, so this all happens at 200 MeV over C. So if you want low energy muons for mu2E or, you know, whatever your favorite muon experiment is, you have 200 MeV over C muons down here with a rather, you know, some nice parameters which you can do interesting things with. And we have 10 to the 12 per second. So if you want to take, you know, a couple of percent of 10 to the 12 per second, which I think is better than what you have at the moment, that would be, you know, I'm sure something could be arranged. In fact, I was thinking about it. We have about, in terms of mu plus to mu minus, we have about 10 or 20% more mu plus than mu minus. Mm-hmm. So those somehow, the collider people say they want symmetric beams in terms of charge. So 20% of the muons we have to mu plus, we have to throw away anyway. So
how much Higgs factory is actually free? So I understand that you say in terms of cooling curve you have to go through it, but it is you know, how much out of the way I have to go?
So in terms of the acceleration, just imagine you have to build a 60 GeV to get to the Higgs resonance, right. 60 GeV electron accelerator, and that gives you a cost scale. You know, so we're probably slightly higher emittance than the electron people, and there are some things you need to accelerate rapidly, but it's probably a lot of the technologies are shared. So it gives you a sort of flavor for the sort of scale of the facility you're building in terms of going to a Higgs factory once you built out the front end.
What's the momentum with 200 MeV at a low point?
So the units here are electron volt seconds. Okay, so if you imagine that you're you're at like what sort of few times, so this means sigma energy times sigma time. Yeah, that's what that really means in terms of the bunch size. So if you, let's say you want, you know, people talk about a few MeV in terms of the energy spread, and that would give you, you know, yeah, that's sort of roughly the energy spread of the Muon beam in the collider.
So that's way too high momentum for the experiment, so we'd have to slow that down while preserving the phase space.
So no, hang on, no, I'm probably being confused. So if you want to build a Higgs factory, the width of the energy spread of the Muon beam at the collision point is like few.
No, if you wanted to give people like me something.
If we want to give people like you something, yeah. So this
That's way too high momentum.
what? So let's say this is 200 MeV. Okay, that's the energy.
20 MeV.
Yeah. Or well, we can probably arrange that as well. But anyway, so 200 MeV, easy enough to slow things down. But the point is that the
Right.
energy spread
Yes.
is, you know, you can make it very long if you don't care about the time.
Yeah.
You can make it long and very small energy spread.
Which is great for the stopped experiments.
Yeah, so that can be arranged. It requires, you have to spend some money on RFCO.
So.
Well, if you've already spent however much this Muon ionization cooling.
I'm saying it's a marginal addition.
It's a marginal addition.
We should talk about that.
Yeah. Okay, I'm going to get told off if I don't keep going. So, right. Okay. So we want to demonstrate the ionization cooling technology. So we want to build a cooling demonstrator. This is the sort of facility we want to build. So we have a target. We go through. Okay. Potentially, we go through a selection system. We take high energy pions off to do something else. Neutrino physics has been talked about. And then we take the 200 MeV pions, let's say, off. We do some clever accelerator gymnastics to make these little 100 picosecond pulses. So the scheme, if we did it at CERN, for example, we would take like a 10 nanosecond long pulse off the PS. We'd do longitudinal, put it through some RF cavities to make like sort of 10-ish, 100 picosecond long bunchlets, and then we would go through and put that into the ionization cooling channel. And we're roughly, we're looking at about 10 to the 6 muons in each of those 100 picosecond, those 10, 100 picosecond pulses. And a spot size is like sort of few millimeters, few MeV over C is the sort of typical transverse dimensions to be. I'm glad the previous speaker, I'm glad we had introduced mice. So the reason we want to do a cooling demonstrator is because mice was a great experiment. I worked on it, so I don't want to, but it was kind of limited in what it did. So we only called in transverse, whereas in this cooling demonstrator, we'd like to call in longitudinal phase space as well. We only had one absorber. We'd like to have many absorbers. We only actually had a section of the cooling cells. This is a picture. We basically had just one absorber sitting in a solenoid channel. We'd like to try and string together several different cooling cells and even into a long line. We'd like to reaccelerate, so we had no RF cavity in this scheme. And we'd like to use a real sort of bunch beam insofar as that's possible. So this is the concept for the cooling cell, which we have. So let's say you have these wedge-shaped absorbers. I didn't go into why we want wedge-shaped absorbers. Unfortunately, there's no time. But solenoids here, and then you put a dipole on as well. Again, I didn't explain why. I lost my. Yeah. Okay. And then we go through these RF cavities. So when we lose beam energy here, that's what does the actual, let's say, non-Liouvillean phase space reduction technique. Then we reaccelerate the beam in these RF cavities, which brings the beam back up to the right energy, and then we repeat. So you can see what I said is we want a nice tight focus at the absorber. So this is like the beam size, parameterized beam size, as we go down the beam line. And so this is the absorber. This is the next absorber. You get this nice tight focus at the absorber. The beam's reasonably well controlled going through the RF cavities, and we get another tight focus. And this is sort of roughly what the solenoid field looks like. It goes up to about 7 Tesla. Where we're still working through the optimization, but this is like our sort of baseline. In terms of the optics, so we don't just care about the amount of focusing. We need to be able to contain this very large beam. And so this sort of gives you a flavor for the beam size that we can fit through the lattice. So let's say we have our working point is between about 190 and 210 MeV over C, where we have a reasonable peak in the transverse acceptance. This is the beam size that we can fit through. So it's like survival probability as a function of distance from the core of the beam. And it's driven, in fact, by this thing called tune, which is where the beam goes near a resonance as you get down to this region. Ask me if you're curious. Okay, one of the technical issues, the main technical risk for this technology, in fact, is the RF cavities. So RF cavities don't like sitting in solenoid fields. What happens is the RF cavities emit electrons just because they're like it's, oh, stop. Okay, so the RF cavities tend to get sparks formed in them when they sit in solenoid fields, which they don't like. We have a couple of techniques to deal with it. One is putting beryllium into the cavity walls. Beryllium is very strong metal. It's very light, low density, which means that it doesn't absorb much energy off the electron. So these electrons, which are trying to make sparks, don't heat the beryllium up, don't make a plasma, and so the cavity's stronger. They tested these at the Muon test area in Fermilab a few years back, and they found that. So if you look at the 0 field option or the 3 Tesla option, let's say this is magnetic field, this is the RF gradient, electric field gradient, which they got, and so they got much lower gradient in the copper cavities when they put a solenoid field on. When they use beryllium, they got a much higher field, much higher field with the much higher gradient with the solenoid field switched on. So that looks quite promising. The other option is to use a gas inside the cavities to insulate the cavities, and that's what they also measured at the end here, and they successfully ran at high gradient. Okay, timeline. This is the penultimate slide. So this is the timeline which we're fighting for. I think it's it's technically limited, and it's one we made in 2021. So what does technically limited mean? So it means that we have the full effort of a major lab. So that means that when something doesn't work, the lab says, well, they don't say, oh, well, you're going to have to sit on your hands until you fix it. They say, what can we do to fix it? So that's what full effort of a major lab means. It means they're really driving, they're finding a way to make it happen. And that's the level of effort we need if we want to make the 2040s timeline. 2040s is important because the high LUMI program finishes in about 2040, and the June phase 2, were it to be funded, will probably finish on a similar timescale. So somehow trying to fight to be the next facility, either in the US or in Europe or Japan, of course. I don't know the Japanese timescale so well. Means making this sort of timeline. So that's what we need. That's how we make it happen. Okay. So I think it's a very exciting time. I think there's a lot going on. There's too much material for me to cover. I didn't say lots of things, but what I did talk about was high power protons, including the FFA R&D, pion and muon production targets and muon cooling studies. And okay, so hopefully I'm looking forward to Thursday lunchtime, because I look forward to further collaborations with the US, and I hope we get a nice result from P5. So thank you.
We have time for a couple of questions.
Thanks, that was really, really great talk. At some point, there was this discussion about this lemma scheme using E plus E minus at the dimuon mass threshold. Is that still something considered, or is it just dead?
It looks very hard. So it's not being really actively looked at anymore that I'm aware of. So things like the amount of beam power on the target to produce the muons, the energy going onto the target looked rather high, and in terms of producing the required number of positrons, that looked, let's say the ILC, people say the ILC positron source is quite hard, and it looked harder than the ILC positron source by. So it's sort of, it looked very challenging. So.
Any other questions or comments? There's a long way to go to the 2040 benchmark. So what's the most meaningful, intermediate step? Is that the demonstrator the most meaningful one? And what's the energy scale and luminosity we're talking about for this?
The demonstrator.
Yeah.
So demonstrator doesn't produce collisions. So it's not got a luminosity.
Just a beam.
It's a beam test. So it's like an accelerated development facility. What we make from this is, let's say 10 to the 6, as I say, 10 to the 6-ish muons per pulse with an energy spread of about 10 MeV over C, a spot size of about 10 millimeters, and a time spread of like sort of 10, 100 peak second along bunches, roughly. That's
And
sort of
what's the energy of the muon?
200
200.
MeV over C.
200. Good. So we should define some opportunities for that.
Absolutely, yeah. I think if we could, and so people talk about taking farms off the target as well at much higher energy.
So far, you just assume that you'll be dumping the muons, right?
So far,
mean,
we assume that we're dumping the muons, that's correct. Somehow, I think it's, so the risk, right? There's strategic risk, right? If it's just an accelerator test, then if I just skip forward to this requirement, right? So this requirement, full effort of a major lab, if it's just an accelerator test, well, it can stray, it can go a bit longer, no one cares, they can let, whereas if there's you guys saying, hang on, we want our bloody muons, then that's a much stronger case. So I think if we could develop a use case for that, I think that's much stronger. So if you guys have that case, then I think that's good.
Any other questions or comments? Not, let's thank the speaker again. We should move. We have plenty of time to further discussions. I hope we find new opportunities out of this workshop. So next, we're going to have LianTao Wang from University of Chicago to give us a talk about physics potential of muon collider. Same as before, let's ask questions during the talk to make it more interactive. You can see
does it work?
yeah,
Okay.
working.
All right.
So Derek will show you the time.
All right, thanks for the invitation. Yes, I will go to talk about physics potential of muon collider, mostly high energy muon colliders. So you have seen this before already in the previous talks. I won't say too much about it, just to remind you that the high energy muon collider, these are the energies we are talking about. There's a 3 TeV benchmark being talked about, the 10 TeV, maybe something else slightly beyond 10 TeV, such as 14 TeV. The integrated luminosity is this, and I think the way that this integrated luminosity going up with energy is so that it follows roughly a scaling with E squared. This is sort of designed to keep the Joule rate, Joule number of events roughly the same, and there is some motivation, but it's not the complete motivation. So the question, of course, on everybody's mind, the first is, are we ready to build? And I'm not the right person to really talk about it. I think the previous speaker say a lot about it already. And this is a slide I stole from Palmer. It's a high level summary, and I think the colliders on this side are more ready, and the colliders on this side are less ready. And the muon collider, I think it's roughly smack in the middle. It's less technically ready than some of the more mature proposals, but I guess it's within the striking distance. The message I can extract from this slide is that we are not quite ready to make a decision to build it yet. Okay, I cannot say we're going to build it yet, but we do need much more R&D because this is such a tantalizing possibility. We do need much more R&D to understand what's needed to build it. Okay. Okay, so, and I think Chris goes through the timeline again as well, and this is another representation of a similar timeline, and we'll have the next 7-ish years to do R&D, and then followed by a demonstrator phase, and then we are at the stage that we are more or less ready. And the goal is to really at that stage by, well, I would say early 2040s, judging by the timeline I've seen. And of course, this needs a lot of support. It needs both manpower and the money. I think this is some of I took this plots from the US snowmass discussion. They're asked for the P5 panel, and there is a international muon collider collaboration already established. There are lots of activity going on in Europe already, and in US there are lots of support during the I think last 3 to 4 years during the snowmass process, and you know, again, US support and both money and the people will be crucial. And as a first step, there will be we'll see what the P5 report says in roughly, I guess, 24 hours. Okay. So now this comes to the main goal of my talk is to say, why do we need a muon collider? What's interesting about the muon collider? And in some sense, it's quite obvious. I think the physics case to me is obvious. As soon as you're telling me the energy and the kind of energy that you can reach, I'm already on board. And so it's high energy, probing shorter distances. This is the energy frontier. I think this is, I hope at least this is good enough for most of us as the strongest motivation to have a muon collider. And so, but still, I think there are lots of other questions you can ask, even why muon collider at this kind of energies, like a 10 TeV-ish scale. So for this, let's just take a brief look at what we are looking at in the coming decade in the energy frontier machines. So we are in the middle of LHC run. It's going to collect a lot more data, maybe still going on for another 2 decades. And at the same time, there are lots of Higgs factory, E plus E minus based low energy Higgs factory being proposed. You know, both in Europe and in China. Also, there is the lower energy version of ILC and the CLIC. So these are all low energy Higgs factories. So the main gist of this bunch of machines, I would say, is going after a very precise measurement, improving the precision as the data accumulates. At the same time, looking for some rare processes. Okay, this is the main goal: precision and there's some rare processes in the next coming decades, I would say. So now the step beyond that is obviously the next energy frontier. So there are 2 options being frequently talked about. It's one of them is a PP collider around 100 TeV scale. Another one is such as FCCHH or SPPC. Another one is a muon collider, which is around 10 TeV scale. So for PP collider, as we all know that we should really the effective center of mass energy is only a fraction of the total center of mass energy. So roughly speaking, these plots are supposed to show you that the effective center of mass energy of a PP collider is at 100 TeV is similar to a effective center of mass energy of a muon collider at a 10 TeV. Of course, in detail, this depends on what actual process we are talking about, what is the pattern and so on. But this is the rough message. Okay, so at the same time, I think the lepton collider is somewhat cleaner, quotation mark here, because also this is a model dependent, so a channel dependent statement. And it is good for precision and search for some of the channels that's difficult for PP collider to look for. Of course, PP collider has its strengths as well. And I'm not going to do a full comparison between pros and cons between these 2 options here. So just keep in mind that they are complementary in many cases. Okay, but still, you can still ask, why 10 TeV? Okay, what is there something special about this energy 10 TeV that we wanted to go to, other than it's a big step beyond what we are probing at LGC, which is a couple TeV. So the question is there a something that I'm expecting to discover when I run some collider at the 10 TeV, or it's guaranteed to discover? Okay, I think the answer is no, and I cannot make you a guarantee that there's a no lose theorem for 10 TeV collider. And at the same time, and as I said, it is a big step beyond the current reach, as we'll see some of the examples that I will show you. And there's a lot of interesting physics topics to cover with this new increase of central mass energy. And of course, a higher energy is of course better. If you give me a 20 TeV, 30 TeV, 40 TeV, I'll be even happier to take it. Of course, but of course this is limited by resource. I think it's a combination of these. Sort of we think that 10 TeV is a more reasonable number for the next step that we should explore. Okay, so for the rest of the talk, I'm going to give you some description what kind of physics topics that frequently people have been talked about as the main physics case for high energy muon collider. Okay, I think there is the obvious case is that obviously you're going to higher energy, you're going to probe new physics better, increase the reach in terms of the new physics mass. And this is just a simple example with the C prime, and but there are many such examples that you can think about. Now, what I wanted to organize the rest of the talk is that try to see that what kind of questions, what kind of interesting physics questions that these increase of physics reach can help us answer. And to do that, first let's take a look at some of the basic physics output. You'll show this plot. You'll see this plot several times. Let me just spend a little bit of time telling you what's on the plot. So this is the integrated. This is the instantaneous luminosity, and this is the translation to integrated luminosity per year. This is the x-axis is the center of mass energy, and these light gray curves is basically what kind of energy and the luminosity you need to achieve a certain physics goal. So for example, if you wanted to produce 10 to the 5 Higgs per year, you have to have an energy or luminosity above this gray line, for example. Okay, this is just a way of visualizing how many things that you can produce, or what kind of physics goals roughly you can achieve at the particular collider. So this is a plot we made for snow mass, so there has other options on it, but the main point is that you see the muon collider certainly achieve most of those goals. I'll talk about most of them in more detail. Yeah, so the main physics program at the Muon collider, there are lots of them, so I can only focus on certain examples. So I'm going to just focus on mostly this couple examples. One is the first one is the Higgs and the electric weak physics. Second one is looking for other new physics at higher energies, and including dark matter and the flavor and the CP. And there are certainly a lot of more cases. It has been quite well documented already in a lot of the studies and reports. Higgs and the electric weak. I think it's obvious that this is important because we don't really know the Higgs very well. We wanted to still explain the origin of the electric weak scale and so on. So there's the standard. I think you probably heard this a lot already. And what's not so obvious is, I think, is what does muon collider bring to the table for doing this kind of precision measurement. Okay, after all, it's the main thrust of muon collider seems to be going after higher energy, higher mass new physics. But as we'll see that the main thrust, the main strength of muon collider of probing this is also because it's running at the energy much above the electroweak scale. Okay. So first, muon collider is a good Higgs factory, a very good Higgs factory. So this is again that luminosity versus central mass energy plot. And now I emphasize the single Higgs production. This is the 10 to the 6 Higgs. And this is how you, assuming 10 years, this is the luminosity you need to get the 10 to the 7 Higgs. So just as a reference point, the Higgs factory, so far the Higgs factory proposals, roughly they all plan a 10-ish year run and with accumulation of a million Higgses. So I think so again, so these red lines are what the muon collider will do, and you see that it can produce much more Higgses running at, for example, running at 10 TeV. Already you can produce more than one order of magnitude more Higgses than the Higgs factories.
It's the Birch line reach 10 to the 8.
That's the 10 to the.
It's not drawn. I'm just asking.
Okay, I'm going to extrapolate the lines here. I guess. Oh, sorry. I actually have a number. Sorry, I forgot. It is on my slide. Okay. So yeah, these are running at a bunch of benchmark energies, and again, assuming the same scaling of luminosity with energy, luminosity scaling with energy square, and these is the amount of Higgs that we're going to produce. And again, on this side, you already start to produce more Higgs than the Higgs factories. Of course, producing Higgs doesn't mean that you can do a measurement. Okay, so this is there are certain unique advantages of doing Higgs measurement at the low energy Higgs factors. Nevertheless, I think muon collider, just because it still has a great potential to the Higgs precision measurement, just based on the fact that it produces a lot more Higgs. And this has been panned out by some of the studies.
Wait, so on previous plot, the lines were for 10 years or for 1 year?
10 years. This is for 10 snow mass years.
Here you're giving us 10. Oh, one snow mass year is only 10 seconds.
10 to the 7 seconds.
I look at 10 here, I get 10 to the 7 Higgses per year, no? Or is one snow mass year only 10 to the 6 seconds?
That's 10 to the 7 Higgs per 10 years.
Yeah.
So it should be per 10 to the 8 seconds. Yes.
Yeah, so that's the upper end.
Yeah, sorry. This is 10 to the, yeah, this is 10 to the, probably. Sorry. Okay. And this panned out, and with some of the recent studies with the Higgs coupling measurement. So this is usually, if you when doing these studies, you'll see a lot of this kind of bar plot. Okay, so this is one of those, and this is the red bar is the high luminosity RGC, and so roughly speaking, high luminosity RGC can do a bunch of Higgs measurement at the several percent level. Okay, you don't want to read this plot in detail. This is a rough idea. So a few percent is what the high luminosity RGC will do, and the goal for the next generation of Higgs measurement is to get to a 0.1% level, so especially for the CZ and Higgs WW couplings, and yeah, so this is what the muon collider can do, and it's factor of 10 than the high luminosity RGC. It's comparable to a E plus E minus Higgs factories actually for these measurements. Higgs factory is especially strong in the Higgs ZZ measurement. Okay. And I think the 125 TeV, not TeV, 125 GeV Higgs factory, its main power shows up here. This green bar is when you have the help of a 125 GeV muon collider. You see that it can improve the Higgs mu coupling much better. That's the one thing that the 125 GeV can do. Also, the width measurement. Okay, Now we are running at one of the advantage of running at high energy is also that you have enough energy to produce a lot double Higgs event. So you see this line is a 10 to the 5 double Higgs. Okay, so right. So there are good potentials for either running at the 10 or 14 TeV to reach a number around the 10 to the 5 double Higgs. This is a very good for this crucial measurement of the Higgs self-coupling. I think Ryuichiro already alluded to that. And this is just another way of saying that this measurement is important. So for example, it tells you something about the shape of the Higgs potential, and it tells you something about the nature of the electron phase transition in early universe, whether it's first order or second order. Okay, so that has other ramifications for other new physics scenarios, such as barogenesis. Okay, so these is just some example models, and these are a bunch of models that's interesting for give you a first order phase transition. And these models usually predict both a deviation in the Higgs Z coupling and in the Higgs in the Higgs self coupling. So there are lines of a bunch of other experiments can do, but I think muon collider can do very well in both constraining this model from the direction of Higgs Z coupling and also from the direction of Higgs self coupling. Okay. Especially in the Higgs self coupling. To give you a very good measurement. Okay, so in addition to the Higgs boson, we are also interested in a lot of other new physics particles that are associated with the weak scale. So for example, if you have additional Higgs bosons, and muon collider is also capable of producing them and have a good reach. And just this is what the LianTao can do, and the muon collider can do much better. And another famous example frequently been talked about is the top partner, just because top quark plays a very important role in electroweak symmetry breaking, and many new models of physics beyond standard model predict there is it goes much slower than I thought. Did I start with 45 or?
It's 5 minutes plus time for questions.
Okay.
10 minutes.
All right, sorry. I'll go a little faster. Okay, so there are famous examples like that, and these things tends to give you decay of top partners tends to give you quite spectacular signals, and which is supposed to be very easy at the lepton collider. So this is we fully expect to reach to above half of the center of mass. So again, muon collider is way overachieved in this. Even if muon collider at high energy at the beginning, we can't really get to that much luminosity to do some of the precision physics, which we should certainly have no trouble of covering the top part. Another interesting thing about running at high energy is that high energy actually give you better precision in the following sense. So if we think new physics is heavy, we can integrate them out, and their effect is parameterized by effective field theory operators. Their effect will grow higher at higher energies. For example, if new physics is leads to some dimension 6 operators, in general, you can find the processes that their effect goes like the effect of new physics goes like E squared. Therefore, if we can measure the high energy distributions of those cross sections better, it gives you better precision because the effect of new physics is naturally larger.
It depends if you have interference.
Yes, exactly. Yeah. So with that caveat, otherwise, yeah. But it's possible to find those processes. You do have a. Yes. So this is for example, in the composite Higgs model, and you can look for example, a dimension 6 operator. This phi is supposed to be Higgses, and the effect of the difference that they can generate, and this is the reason why muon 10 TeV collider is so much better than than the others. So this can do precision measurement of the tails of those scattering processes. But another example is a top quark Higgs coupling, so this is if we think about WW to TT bar processes, right? And if there is so this is sensitive to the top quark Yukawa coupling, and the new physics can certainly modify this coupling. And so this is the largest. By the way, it's interesting because this is the largest Higgs coupling, right? So it's very certainly plays a very important role in electroweak symmetry working. And so the new physics can be parameterized like this. It will lead to a amplitude also grows like energy, not quite energy sphere, but energy. Okay, so this is again another example of going to higher energies. You expect to get a better precision to probe this kind of new physics, which is again you see that the muon collider, the 10 TeV can probe this to better than 2%, which is better than some of the other options. It's comparable to FCCHH. Okay. This is another point about running much above the threshold for electroweak scale, and which is you are expect to produce many electroweak gauge bosons, and they are almost massless and so on. So there are significant rates in producing 3 of them, 4 of them, and it will be sensitive to higher order new physics. Okay. Let me just now let me talk about dark matter. And there are many dark matters. I will be just talking about WIMP. I think most of you are familiar with this story. I won't go over it too much detail. The simplest model is that the WIMP is one of those is one member of the electroweak multiplet. Okay, so this is very predictive because it's force between the dark matter and the standard model is mediated by standard model weak interaction and WZ and H. And so there are 2 famous examples where the WIMP is electroweak doublet or electroweak triplet. These are the simplest examples. And I should say that because this is very predictive, the only free parameter in here is the mass of the WIMP, basically. Okay, and that you can ask what mass of the WIMP you need so that you actually have the correct dark matter abundance. And these turns out to be at least several TeV, but sometimes even much higher scale. Okay, this is certainly way beyond the LHC reach. Okay, and on the other hand, we should try to cover this. This is an ideal target for muon colliders to high energy muon collider to cover.
You often have like charged cousins, right, on this dark matter.
Yes, I'm going to talk about it. Yeah, it's actually very important for the signal. Okay, so so there are 2 classes of direct signals at the search for the colliders. One of them is an inclusive search for dark matter plus something else. So sometimes called X plus mat signals. So yeah, so these are, for example, it can recoil against the photon, or it can sometimes it actually because you can have a lot of photon radiation in the muon collider. You can think about them as a photon mu collision. This will give you a signal which is only 1 muon. So this is a mono muon signal and so on. Okay, the challenge for this channel is there are lots of background and lots of system effects. There's the second kind of signal which Maxim already alluded to, that you have a much higher rate to actually produce their charge partners, and the charge partner will decay. But because the mass splitting between charge partner and the dark matter is very small, that decay is longer. And so what's going to happen is this: you're going to have this so-called disappearing track signal that with the charge partner travel some distance, make a few hits in the tracker, then disappear. Okay. There are also challenges. This is a very unique signal, but there's also challenges. So the detector needs to be close, okay, close by the interaction point, so that this particle can reach the detector before it decays. And there are also lots of beam-induced background because these are soft tracks and soft signal. Okay, but nevertheless, I think a lot of study in this two class of signal has been done, and they show very good promise. Again, so these black bars are the so-called target mass, that the mass you need to reach, so that this can be thermal relic abundance. So in both the Wino and the Higgsino-like case, you see that even with the inclusive search at the 10 TeV collider can already cover some of the thermal target, and with the disappearing track search, it can cover all. So a 10 TeV muon collider is already enough to give you a conclusive conclusion in some of these simple dark matters, which is way beyond the reach of the current LTC searches. Yeah. Anyway, so let me not too much since I'm 0 minutes. I still have one more case to say. I still have 5 minutes, or okay.
Yeah.
No.
Yes.
Okay. Sorry. I'll go fast. Okay. I don't have too much. So the last case I wanted to mention is the flavor and the CP. So I think it's a very long-standing question in the community. Is where's the flavor structure of the standard model coming from, or sometimes the more specific is what is a slightly different question is what's the scale of new physics that carries new flavor structure. Okay, so what are the new flavor CP physics? What is that scale? So there have been many measurements over the decades that has not seen any new flavor violation or CP violation beyond the standard model. Such as lepton flavor violation is more relevant for us. And there's also kaon flavor, kaon and the B's, but also EDM measurement. Okay, but this has consistently pushed the scale to be far beyond the weak scale. Okay, so I think therefore it's for now we have a thinking. When I'm thinking about the higher energy collider, it's natural to ask the question: what's the potential? What are a high energy muon collider can add to this picture? Okay, so these are just some examples of lepton flavor violation. So for example, mu23E is already putting about more than 100 TeV, and tau 23 mu is more than, it's weaker, but it's around 10 TeV. So at the direct probe of both of these set of operators, in principle, not this particular one, but direct probe of this operator is possible. This one is also possible if I replace the second factor with mu's. Okay, but this basically is looking for signal with mu plus mu minus to a pair of leptons with different flavors. Okay, so this is a probing effect EFT operator. Again, its effect is supposed to grow with higher energies. So muon collider should be able to reach to an energy scale much beyond its center of mass energy with these operators. Okay, and this is again panned out by some studies, and this is trying to focus on the tau mu channel, and so it give you some bounds on depends on the center of mass energy of the muon colliders. It give you some limit on this operator to roughly about 100 TeV at around the 14 TeV muon collider. Okay, so this is roughly comparable to what we have now for the mu23E operator, and a big step beyond what we have now for the tau mu flavor violation. Okay, right. So I think at least there is a good potential, and of probing this kind of operators at the muon collider. Okay, of course, we don't have to assume that the mass scale is literally the mass scale of the new physics. So there could be additional suppressions such as flavor symmetry, or whether there's some more commonly there's some loop suppression. Because the new physics corrections to the flavor changing process may come only in the loop order. Therefore, the mass is much lower. There will be opportunity to see those things directly in that case. A typical example is Suzy has the flavor violation just in the muon and the selectron sector. And they give you, for example, to the mu to E gamma process. And based on the current limit, this puts M SUSY already greater than, with some assumptions about the mixings, but put M SUSY greater than above the TeV scale. And at the muon colliders, we are going to going after this by looking for processes with lepton pair production with mu-E production. Okay, so this is a study by Matt and the company that's showing you that yes, we can actually help them. So this above this band, above this red band can be probed by the muon, basically. In comparison with some of the other experiments. And these shades is some preferred model parameter space, which I don't get into. And EDMs are also quite interesting. There are many ways that the CP violating phase can enter EDM. And this is a particular specific set of diagrams for the bar Z type of diagrams. It contributes to EDM at the 2-loop order. And what's interesting about this is that literally the same diagram can be probed by at the muon collider, the mu to 2H production. Okay. All right, so this is at the end of my talk, and let me just conclude. And I think high energy muon collider holds the promise of getting to the next, really a very promising way to get to the next energy frontier, around 10 TeV. There are lots of interesting physics to cover. I can only scratch the surface here. There are lots more, but I was not able to cover. I think my hope is that we'll do very solid R&D in the coming decades to make this into a really mature project. Okay, so for the best. Thank you.
Thanks, Anton, for a nice talk. And questions or comments? Everyone is fully convinced about Muon.
Yeah, thanks for the talk, LianTao. So you had a few slides about WIMPs and you listed some thermal targets.
Yeah.
How many of those have already been ruled out by direct detection, or are they all too heavy that direct detection would
Most of them are too heavy. No, I don't think. Sorry. Let's go back there. Yeah. So direct detection is the strongest when the WIMP mass is comparable to the nucleus mass. Okay. And these are all in the limit in that line region that the limit just scales like 1/m. So this is relatively independent of mass. So the question is that what is the direct detection process of these guys? And these are I think these are all one loop mediated.
There is a subtlety, right? For many of these models, it's killed because there is a 3-level Z exchange. But once you start having like a small perturbation to the mass and split the Dirac fermion into, like, say 2 Majorana fermions, you're done by the loop level, by the quark mass, and so.
Yeah, thank you. Yeah. This Maxim is pointing in particular with this case, right? This case is ruled out by many order of magnitude if it's a pure Dirac. Okay, so in SUSY, for example, if this is a pure Higgsino, there's nothing else, then this is ruled out. But if you just need a tiny bit of mixing with a Bino, like a Bino with 5-6 TeV Bino, and the mixing is very small, you will not otherwise, but it generates enough mass splitting so that you don't have elastic scattering. You only have inelastic scattering. Then suddenly this is not ruled out. So, okay, so this is the case, and for the Majorana case, then it's obviously fine. I should say that there's another one that there's another constraint from indirect detection on these guys. Okay, so because these guys can annihilate in the halo, and the dominant cross section, for example, for the V node is to WW. Okay, that's somewhat diffuse, and so it's difficult to do. But there's a distinct signal where we know annihilate in there's a loop to 2 photons. These are very strong line photons. And now if you take the standard halo profile, okay, and this is already being constrained by the direct detection, but indirect detection. Okay, but that's depends more on on the halo profile. So the Higgsino is safe.
So back to the lepton flavor violating topic.
Yeah.
So something that Matt et al. Didn't cover was mu minus n to e plus n, which is something that we think we can do 4 orders of magnitude better.
Sorry, what's
mu
that?
minus n goes to e plus n star.
Oh,
Right.
mu minus goes to e plus.
Yeah, that's a definite possibility that we can improve that 4 orders of magnitude also,
Okay.
which couples to different things, right? And I think it should get included in future papers
Sure.
on the
Okay.
topic. So I should tell Matt that, I guess.
Yeah, yeah.
I'm not the expert, but is there any motivation to prefer TEB WIMP compared to the low energy?
Yeah. So the motivation is here. The motivation is basically it's simplicity. Okay. So there are 2 ways. So we know that we'll have to add a new particle. Okay. Now, if you just add 1 new particle, you still have to add another interaction. You have to tell us how do they interact with us. Otherwise, the WIMP story doesn't work, right? So there you have to like and then here what you have to do is I just say I'm going to add 1 electroweak multiplet instead of a singlet. Okay, if you just add 1 particle, it necessarily means I add an electroweak singlet. Okay, now I just add an electroweak multiplet. It's if you want, I just add another lepton. Right, it's a neutrino component can be documented. Okay, so then the only free parameter there is its mass, because its interaction with the standard model is fixed by standard model gauge symmetry. So I think that's the main motivation. That's why I was simplest is a little bit objective, so subjective. Okay, but it is by my standard. I think this is very simple. Yeah.
Okay.
Can you also comment on the, do you have a feel for the errors on these numbers that for the thermal, like for indirect, it took n and a low resummation to get to like a 20% on the cross section. So should I assign 20% or more or less?
I don't have that number. I mean, we can go through some of these.
No, I understand. Just maybe you knew. Okay.
Yeah, I don't. Yeah.
Okay, so we've had lots of discussion already. If more questions, we can continue discussion afterwards, but let's thank the speaker again. So we have many locals around here. For our lunch plan is to go to the restaurants. There are many restaurants near campus, so we can just gather outside. People automatically split into groups and go to different. Okay.
We leave our stuff in this room, or should we take it with us?
Let me ask our admins.
It's a visible R bar. Yes, you can leave your side. That's what with some like thing.
And we'll reconvene.
Yes, come back to 2013.
Yes. It's and then there's also
no, this is quite small, but that's not clear.
but that's the problem.
In the last couple of years. Yeah, I hope
I don't have a good sense. But I can look at this.
ADS. They gave up. Now they include gravity and resonance, and then they raise it up, they put filings, and they use